Hello, everyone. Welcome to the Audio Product Development Alliance. I'm Roger Shively from Shively Acoustics International, and this is the APDA, your gateway to audio product development. Today's topic is audio zones and sources, separation, and much more, and all of that in real time. Joining us today is from GPU Audio is Sasha or Alexander Sasha
Hello,
Talashov.
everybody.
And we also have Sergey Korobov. So,
Yeah. Hello,
hey,
everyone.
Sergey,
Hey.
welcome to you both. Also, in addition to Sasha and Sergey, we have joining us from the APDA online is Dave Lindberg from DB Enterprises and the THD podcast. How you doing, Dave?
Hey, good
And
morning,
also,
everyone else.
and Steve Willenberg from LinkPlay is here. Hi, Steve. How you doing?
Good. How you
Uh,
doing, Roger?
Good.
Happy to
Our
be
media
part of this group.
partner, yeah, good. Our media partner is Audio Express, and that is supported by Joel Martins and Adam Levinson from Levinson Consulting is also our partner and supports us. If you don't know the APDA, the APDA is basically is also an organization that is focused exclusively on audio product development education, providing current relevant content that can be experienced in person, live online, or on demand, and combined with a valuable cross-section or cross-industry knowledge sharing. The APDA serves as a networking hub for the audio industry, offering access to experts and colleagues for professional development. And essentially, the APDA is where we come to learn how to build relationships and build better audio products. Here we talk about design, we talk about measurement, simulation, supply chain, automotive applications, headphones, earphones, and wireless technology. And we even touch on standards. So, with no further ado, we'd like to thank Spencer for helping us out produce this today on the live talk. We're recording it as well and it'll be on the YouTube channel later. You can share that, rewatch it, join us often, and like us. And also, if you can and would like to continue supporting us and joining us a little bit, you can. We ask you to join our APDA WhatsApp group. We'll be watching the WhatsApp group for messages as well and during this live stream, but we'll be watching the chat in the YouTube as well. So if you have comments or questions, you can leave them in either place. So just so you have a chance to ask questions and find out what more you want to know from us. And later on in the YouTube channel, you can leave a comment there as well. So Sasha, welcome. You are the co-founder of GPU Audio. And I think it'll be interesting today to share not only the technology that you're going to share, that we're going to have plenty of demonstrations, I understand, but maybe also a little bit of the story about how the technology that's behind GPU audio came to be built, and maybe talk about that as well as what this experience is going to be like in this multi-zone audio with active, underlying active zones compensation. So I'll let you kind of start us off, and then we look forward to some of the demonstrations that are coming up. So welcome,
All
and
right.
let us know a little bit more about yourself and also GP Audio and how this came around and what it is.
Sure. Sure. Thanks, Roger, and thanks, everybody. I'm very glad to be here. So, a little bit about ourselves, company, and how we ended up here in the automotive audio. So, first of all, we're a team of 18 people. We're mostly based in Europe. I'm based here in California, in Cupertino. This is where we have our demo vehicle. We're going to present you something today online at PDA episode. So, first of all, we are the world's first and only company who unlocked GPUs and NPUs for real-time audio computing. Typically, they were not GPUs and NPUs were not designed. Is this the echo coming from me? Pardon me.
I hear a slight echo,
Still?
but I'm okay. You're all right.
Okay. Awesome. I'm trying to see whether it's still me or something is going on. Just give me 1 second. I'm trying to
Okay.
do something on my end.
I think so far it sounds like it's doing all right. I don't hear it too badly at all.
Okay.
I
Okay.
think
Let's
we'll be okay.
just continue.
I think we'll be okay. Yeah.
All right. So we're the world's first and only company who unlocked GPUs for real-time audio computing. As you know, GPUs were designed to work, let's say, 60 frames per second, right?
Mhm.
That means every frame has to be processed each 16 millisecond latency So you have to come up with a solution how to work with them, let's say 1 millisecond latency, which is a golden standard for the pro audio and many audio specific application fields, right? So that's one kind of the fundamental limitation you have to deal with when working with the audio. That's what we solved. Another fundamental, I would say not the issue, but like the entire foundational layer we built when we say we claim we build the entire technology and platform to unlock GPUs for real-time audio computing is that most of the classic DSP algorithms and neural networks, they were not specifically designed for real-time audio computing because their classic DSP algorithms, they are inherently sequential. They're not good fit for massively parallel architecture such as GPU, like these, let's say, infinite impulse response filter, right? In the direct form, it's not a good fit for massively parallel architecture such as GPU. You have to come up with advanced representations such as state space format of filter to be a better fit for GPU architecture. So you have to reinvent the math, and then you have to code it for a variety of the GPU frameworks that exist, like NVIDIA CUDA, OpenCL, or whatever you use. That's what we also did in order to be able to do something very new to unlock new consumer products, innovations that we can deliver. And this is something that we want to show. Oh, the echo actually gone. Something.
It's okay.
Yeah.
I got tired. It
Awesome.
got tired. Yeah.
Yeah. So that's what we did in terms of the innovation. It took years of my life, and it took $12 million of venture capital investment.
Yeah. So you began this. What was you gave us the idea that you needed to improve multi-channel streaming or instead of a sequential use, a sort of a parallel use of the information. What was the first thing that you started to accomplish with that on? You realized right away it had to be on the GPU instead of a CPU.
Right.
I'm assuming. And then what was that first step and how did it come about? Was it working right out of the box for you, or what were you trying to figure out right away?
So it started a long time ago, but we usually say that we started in 2021, 22nd year, where we originally appeared in the pro audio industry. And the very first thing we ever released was just a FIR convolver. And a convolution-based reverberation is the first product we ever released. This is just a plugin, a VST plugin that we released for the pro audio users. And you essentially, as a user, you can install this. You could install this plugin, and you can run a few hundreds of those FIR-based convolutions on your laptop, whether it's MacBook or NVIDIA or whatever, under any operating system. It works cross-platform, low latency, and so on and so forth. That was like the very first real use case we ever achieved with our technology. And then we started tinkering about, okay, we built the entire plethora of those different classic DSP functions, dynamic range compressors, whatever stuff. What kind of true innovation we can build so everybody can actually understand this, not just like pro audio users, like niche products, right? What kind of the consumer product we can bring to the market. And by end of 2024, we decided to enter the other market, which is automotive market. So we are quite new to the automotive audio. And this is how we ended up with the journey together with Sergey, my colleague. going to China, so our first market, almost every single month. And this is where we learned that the whole idea, like a Saint Grail idea of enabling personalized audio experience in car cabin is something that everyone was looking for many, many years, I would say even a decade or maybe even more than that. And on practice, nobody didn't achieve yet. Like no other companies, I will not respectfully not call the names here, but nobody didn't achieve this via the hardware or software, etc. There is no practical solution. Typically, the way it currently companies, engineers currently try to solve the challenge how to create like zones within the vehicles that try to overlap sound with more sound. So, for example, if you ever been in China, there's like Lixian, Li Auto car maker, or like Huawei S800. You can sit in this vehicle, and what essentially can have as experience, you can have like loudspeakers embedded in the headrest. And these loudspeakers can be used in, let's say, during the phone calls, right? And for the driver, during the phone calls, you can share the phone call as a driver. And for the rest of the people, you still can have some of the other zones audio played back, let's say, for the rear zone. But you still experience the audio bleeding in each other zone audio because there is no active zone compensation, right? The sound attenuates naturally within the car cabin. It's very limited space, and sound propagates freely, reflects from each kind of the surface, and so on and so forth. So nobody could ever solve this problem, and we know why. And we saw a lot of the, I call it ugly design solutions, where there's like, I saw in the hallway, they use this, how to say, like a screen, like a shield, a shade between the two zones. So they kind of tried to separate those zones with their physical barrier. So that looks funny, but it never works. So you need to apply active zone compensation at the listener's head position. This is what we have achieved as a pure software solution.
Got it. Okay. All right. So maybe it's not as clear to some why it wasn't working, but there was no constant adjustment of the sound when you had a different source of noise or music. It's basically what the problem was, still is, until you come along and can do that real time. You're doing real time compensation so that if there is a noise, you can take it away, and when it changes, you have control over that, as opposed to what may have been a static solution for most implementations for this. Is that correct? That it wasn't real time? Yeah.
So the problem, so there are many aspects of this problem, I would say. We as a company and as engineers, we see the main aspect of this problem is actually computing. The real problem is that in cars today, you have before GPU audio, you had only two sources of the computing power. The number one source is a single CPU core. You usually have allocated for all kinds of the audio software that needs to be launched simultaneously. So that means you have a very tiny, I don't know, like 10% CPU utilization of one single CPU core that you can do whatever you want to do with DSP functionality. You run like a bunch of bi-quad filters, whatever. And then you have the choice of running, let's say, DSP, digital signal processors of Qualcomm Hexagon. Let's say you have a Qualcomm SoC and you have Hexagon as a part of this SoC, or you have analog devices, Shark processors. So the problem with those DSPs, even with the Qualcomm Hexagon that received a recent update, there are, in comparison with the GPU, there are extremely slow in terms of the processing, and they cannot do heavy processing in comparison with GPU. So just to give you some numerical comparison, okay, to make this technology work, and as we will demo to you today, to enable this software as a software, we use for 15 stock loudspeaker Cybertruck setup. Cybertruck is our demo vehicle. So what we did is a rewired complete setup. I'll show you very soon. For the stock, 15 loudspeakers. For the two-zone audio stereo, so that means 2 multiplies 15, we run 60 convolutions real time. So ADI Sharks, analog devices Sharks, if you look into the spec sheet, can run like 3 fast math hardware accelerated convolutions simultaneously, maximum. Qualcomm Hexagon, I don't know, maybe 8. A single CPU core, I don't know how many. We didn't run the test, but very limited number. So we couldn't manage to make it work on the single core CPU, a few core CPU, but we managed to make this 60 convolutions running real time, just taking 2.3% of the Adreno 690 GPU of the 4th gen Qualcomm SA8295. So for those people who work in the automotive industry, they know this is most popular SoC you can find in mid-tier plus vehicles all over the world, so to say. It's like regular 4th generation SoC. So we take just 2% of the GPU power to implement this kind of innovation that was impossible before, and that is completely impossible by DSP and single core CPU.
What was the GPU that you mentioned before that you were using?
So we use the infotainment system GPU, like the computers behind the touch screen.
Okay.
Qualcomm, it's Adreno GPU. So typically GPUs that automotive car OEMs already purchased. So they're already there in the cars, sitting there doing almost nothing most of the time. So in fact, they're underutilized. And it's very rare where the GPU utilization hits more than 30 or even 70% if you run like Unreal Engine powered beautiful 3D GUIs with all AI assistants, AI workflows, whatever you do and engage with your car system, whatever you do. We always can take like 2% to run these amazing things like multi-zone playback and even more powered by our platform.
Got it. So it's Adreno, ADRENO. Correct?
Yes.
Yeah.
Yes.
Yeah. Sounds good. Okay. And it's just sitting there.
Maybe I'll just
Go ahead,
jump
Dave.
in to dumb this down a bit. So in just generalized terms, you're creating isolation within the cabin, so you could perhaps have 2 people on a call and 2 people doing something else within a 4-seat cabin. Is that
Yes.
roughly
Yes.
what we're talking about?
Yeah,
Okay.
that's usually the use case when we get to a car, or at least the desired use case.
Right.
Yes.
So this parlays into conferencing and all other kinds of applications as well.
Exactly.
Yes. So
Okay.
So we're agnostic to whatever the source of the audio that is wired in software-wise, so to say, SoC-wise. So our solution works on the operating system hardware abstraction layer. If we speak about Android or if it's Linux also, doesn't matter where we exactly integrate. And it doesn't matter what kind of the audio streams that go to our post-processing active zone compensation, post-processing unit, so to say. We only need 2 things to pinpoint. Number 1 thing is where we can obtain these audio buffers that needs to be compensated to each other. And number 2 is where we can have access to the GPU resource through the GPU driver. Whether it's OpenCL framework or Vulkan API, we practically don't care the way we need to program a GPU. We know how to work with GPU real-time low latency with our core technology underneath that allows us to do so.
Okay. Yeah, we've got 2 questions, 2 comments. One, Dave, you need to turn your volume up a little bit. And
Okay.
And the comment was 2% is a lot. Is 2% a lot?
Well, where you have GPU usage of the regular system, I think I know from where my echo goes. Maybe Dev, is that from you? No? No?
I think
Okay,
it might be
never mind.
today. I'm not sure.
Don't worry about
No,
that.
never mind. Never mind. I'm sorry. Never mind. Okay, so 2%, 2% where you still have 30 to 70% left. I wouldn't say it's a lot to allow you something. The other hardware that you typically pay for, let's say $50, $100, to just enable something very specific as a functionality, it's a lot. It's just a pure software. So you cannot. Sometimes you cannot make another additional CPU core dedicated to entire software. So we don't cause any stuttering, any freezes. We actually don't cause any trouble. We just take this dynamically whenever feature is allocated, and boom, that's it. If the feature is disabled, we don't take it.
Okay. Okay. That's great. So I'll let you continue if you want to set us up for what's coming. Maybe I think we understand the use case. Maybe Dave, did you get that? Because it's typically what the use case is in the vehicle, which, as you say, can be into any use case. But this one sometimes is the hardest one because we're stuck at a distance, which is good and bad, between the passengers. It's bad when you can't overcome that distance and you have to try to mask noise instead of get rid of it. And so that's one of the things I think is the advantage is if you can overcome the static nature of being too far away from each other or not close enough. I think that's part of it. And then when things change, you have this ability to instantaneously do that. One quick question maybe also is in mind. You said 15 loudspeakers. Do you need 15 loudspeakers?
No, not actually. And I would like Sergey also to speak. So Sergey, can you tell a little bit more about our solution, the requirements, and how it can be deployed to the virtually any vehicle model, and how we see this can be scaled and deployed to virtually any vehicle, mid-tier plus, to the multiple regions, any vehicle size, any SoC, as you know it.
Yeah, of course.
Okay.
So let me start with two main advantages our platform and technology brings to car OEMs. So the first advantage is scalable and flexible platform, which allows very fast implementation and development and implementation of the new audio products. So we all talk about software-defined vehicles, right? But we still don't have software-defined audio in these vehicles, right? So it's still based on pretty old DSP chips. And what car OEMs have to do, they just increase the number of these chips. So with our platform, we mentioned the flagship product, which will be demonstrated today. But going forward, this platform allows implementation of new technologies and new products like real-time noise cancellation, AI-based audio features, also real-time multi-sound source up mixing, and many more actually. And we have a whole DSP library of components already ported to our platform, which allows the car OEMs implement the products very quickly and easily. And basically, the way we came to our flagship product, which is multi-zone playback, is that we see that especially in China, and in many cars, there are so many sound sources, right, and audio sources. And even like in some of the cars, we see several screens. Like we see kind of couple of the screens on the first row and one or two screens on the second row. But still, playing the music or TV or cartoons or whatever at the same time for the first and the second screen is still not possible. So Sasha mentioned that some of the car OEMs, they try to resolve this issue with like even physical separation, but obviously it doesn't work for 99%, 99.99% of the cars. So with this product implemented, we see that like having multiple different sources played at the same time on the first and second row is quite possible. And obviously it requires compensation, zone compensation, which can be implemented only with GPUs. Talking about more details on what Sasha mentioned, that really implementation of this product, of this platform and multi-zone player, it is quite possible for almost any car. So we're not talking only about like huge vehicles, like 3-row vehicles, but having around 12 speakers and more, and like mid-size car. It can be sedan, it can be SUV. So even for that cars, the multi-zone separation works very well. So that's kind of very easy to implement, and it can be implemented to so many cars. And the second advantage, the very important advantage we bring to the car OEMs is substantial cost saving going forward. So today they can launch this product and the platform on their current hardware, right? So still keeping the DSPs in the cars. But tomorrow they can launch a car with no DSPs, right? So using just GPU chips. And we see that obviously every year the GPU chips in the cars they becoming more and more powerful. So this utilization, which is 2% now, it can be even less tomorrow, right? It can go up to 1% of the GPU power. So this that kind of cost savings is essential for the longer term strategy of the car OEMs.
So I have a couple quick questions. Architecture, when you say a number of speakers, are you talking about speakers that are mid-ranges, woofers, tweeters? Are they door speakers, instrument panel, headrest? What is the architecture that you're talking about?
Yeah, there is no requirement for headrest. So although we see more and more cars with the headrest speakers, it's not an essential requirement. So when we say 12 speakers, we assume that, let's say, one is subwoofer, one usually is the center, and all other speakers are door speakers. A kind of very basic kind of structure.
Okay, and the other part you say, okay, you can implement it on a CPU or DSP, but then how is it managed that you do it that way? Or it's just because if you have enough CPU power, you can do it. Is that what you're saying? Or speed?
No, that's probably what Sasha mentioned. The CPU.
Yeah. So when you say
Sasha,
I can put it on existing DSPs right now and then go to a GPU, how is that implemented exactly?
So what we had when we compared, so we had created where we had created the first version, we also created so-called benchmark, the computing performance benchmark, and we tried to compare the GPU naive implementation with naive CPU-based implementation. We tried
Okay.
to compare X to X as much as we could, even though these are different architectures, right?
Okay.
So I don't recall the exact numbers, but I'm trying to be very close to what I memorized. So I think it took from regardless how many CPU cores we have in 4th gen, SA8295 of the Qualcomm, it took 2 or 3 full CPU cores, 100 CPU usage
Okay.
to make it work for
Okay.
the one software instance, okay?
Mhm.
And it's just for the same GPU on the same SoC board, it took 2.3% of the current implementation. And it may take less if we optimize a bit. And it will take certainly way less for the 5th gen GPU because it just gets stronger with each year. And certainly it takes way less for the other GPUs, let's say of AMD and NVIDIA or any other GPUs that are on the market because they're much more powerful than Qualcomm's ones.
Yeah. So and if you use right now, you reference the Qualcomm Adreno, I think is what it was called. Is that an affordable chip, or is that a chip that exists
Oh,
right
yeah.
now? As you're saying, it's something that exists in the display, the head unit or the command unit, whatever you want to call it today, and that's why
Yes.
it's there. Okay. That's one of the things I was going to ask as well. And then the last question is, and maybe it's a comment from Sergey, a software-defined vehicle, audio is in the car right now through software, so it is somewhat defined by systems like QNX or AudioWeaver's implementation of audio features. How are you saying that it is? Can you maybe clarify your statement on, there's no audio-defined vehicle yet? Um, there's no, what version of an audio-defined vehicle do we not have today?
Yeah, well, we said that we can provide an SDK to the car OEMs, right?
Okay, yeah.
And the car OEMs, based on our platform, they can build the service, the products which are not
Mhm.
possible today,
Okay,
right?
all right.
And it's kind of very simple implementation and very fast also implementation.
Okay.
Because the platform is scalable and the platform is very flexible.
Okay. No, I understand. I just want to make sure we clarified that, because if you think about it, there is some software-defined audio in the car. It's just not to the scale that you're talking about.
Yeah.
Okay. All right. Sounds good. Do you want to try to go ahead from here, Alec, Sasha, and demonstrate
Yes.
some things? I think it's a good
How
time.
we would like to approach that. So we have our DJ today at Basil. Basil, please do not share the audio yet because I need to show the setup and explain the setup. What I'm gonna do, I need just 1 minute. I'm gonna head to our Cybertruck vehicle. So I need to reconnect. Please bear with me for 1 minute. In the
Okay.
meantime, Sergey, please speak a little bit about the advantages of the GPU audio platform. So the software such as we have today that can be deployed with OTA updates, it can be integrated virtually from everywhere and so on. And I'm gonna get back to you very shortly. Thank you.
Okay. All right. We'll wait for you, but go ahead, Sergey.
Yeah.
And I think
Yeah,
you were going
well,
to see a
talking about
Cybertruck.
another kind of advantage, the platform, yes, it is purely software, all right? So when we come to the car OEM, we're saying you do already have GPUs in your cars, right? And we see that like every next year, the more and more cars would have that kind of GPUs. It may not be Qualcomm, it might be MediaTek, it might be AMD. So we are agnostic. It might be Samsung. We are agnostic to the manufacturer. All right, we can port our platform to virtually any GPU which is used or planned to be used in the cars. So when we come to the manufacturers, they do already have the speakers, the GPU in the car, and so they don't need any new hardware. So we just take the car as it is, we implement our platform, all right, and it can be upgraded over the year to existing cars, to the cars on the roads. That's very important. So we're not only talking about new cars and the development or implementation of our technology only for the new cars. That's very important.
Okay, that's good. And I think Sasha mentioned that you've had some interest and activity in China, which is sometimes leading us in Europe and the US and North America. And are they using it the way you're describing it? They're taking the GPUs, or are they planning to do that?
Yeah, we see that in all mid-range and higher cars, they already equipped with, in most of the cases, with Qualcomm platform, right?
Mhm.
Yeah, so when we see what's happening on Chinese market, we see like the development from scratch of the car, the whole cycle of the car development is now about 1.5, 2 years. All right. So although like in Europe and the United States, it's still like 3, 4, 5 in some cases
Okay.
years. I mean,
Yeah.
so yeah, they're much faster. They have so many different car OEMs, right? Most of them, as I said, they use modern infotainment platforms. So they have everything to have this technology implemented as quickly as possible.
Okay. And I see Sasha's back.
Yep.
He's prowling around a Cybertruck, I
Yes.
think.
Hello, everybody. Can you hear me well?
Yeah, we can. You're coming in good.
All right. I also hope that you can see me. So
Yes.
we have my partner here today, Basil. Basil, again, please do not share the audio yet. So
Okay.
because we will have a really bad loop back if he'll share the audio right now. I'm gonna explain to you what we have in setup, okay? So this is our demo vehicle. So pardon me for a really mess. It also serves a purpose of the acoustic lab. So let me tell you a bit of the story first. So why Cybertruck? This is a horrible vehicle, first of all, to say. When speaking acoustic-wise, it's just a huge kind of glossy, made of glass prism. So the acoustic properties of materials are just absolute worst you could have in terms of acoustics. But there are very few vehicles available in the US that has these are very necessary two things for us, which are electric plugs. So it's like the choices are F-150 Lightning,
Right.
Cybertruck, and maybe a few other vehicles, right? So
Right.
essentially, you need a huge vehicle and trunk to host all of these, incorporate all of these hardware. So let's start with the setup. Let me explain to you what this vehicle is made of. So the layout of the vehicle is very asymmetric and disproportional. The vehicle itself was designed by Tesla and built in mind for the two front passenger and the driver, okay? That means you have the loudspeakers right here indoor, the big one, another one here, another one here. So on the opposite side, another 3 there. That makes it 6. And the sound bar with another 3 there. That makes it 9, right? So there are 9 loudspeakers over there, right?
Right.
So on the back, it's actually a horrible case because you only have all frequency door loudspeaker right over here. And the only thing you have is right over there, this tiny little one mid-range, okay?
Right. So you have 2 + 1 in the middle and the back.
Yes. And you also have a subwoofer right over there under the seat, under this material. So, and that is, believe me, that is imperfect, not just for the compensation purpose, but just for the playback purpose, right?
Yeah.
So let's talk more about the setup itself. Unfortunately, I cannot share you the pictures of how we rewired the whole vehicle, but I
That's
can
okay.
probably share it afterwards. But you can essentially see some of the wires right over there, coming from here, going all the USBs coming from to this laptop, as you can see us all here to the laptop. This is our current computing unit for this demo
Okay.
case with a bunch of the XLRs coming in and out from the vehicle. I'll explain to you further.
Okay.
And essentially the whole rewiring, all the 15 loudspeakers were connected directly, hold on, directly right
There we
from
go.
over there. Yeah, they're going right into this rack.
Okay.
And in this rack, what we have here is the huge external amplifier. We have 16, one channel is the dummy one, obviously, 15, 16 switcher, where there are 3 options for it. The option A is a stock audio system touchscreen option, where you switch it on, you can hear whatever touchscreen SoC infotainment plays back. Where you turn it down, you can actually hear whatever you connect through the I/O external amplifier and to the computer, which we will essentially hear today, right? And there are a bunch of the multi-channel interfaces, which is Motu and RV, that makes it all things powered up.
Okay. Yeah.
Believe me, these dead weights, they're also important part of the vehicle setup, just to make it work. I mean, the dead weights, the gym dead weights, they're
Yeah.
also a very important part of the acoustic lab. So we usually take the hardware units and we put them right in the second rack here, but it's all empty today because if we put like Qualcomm platform or NVIDIA platform there, it will be a Linux environment.
Got it.
And to demo from the Linux environment will take ages for you to set things up and just to make it running, because it's like embedded Linux environment and it requires a lot of the setup, configuration and stuff. So we prefer just to go with a Windows-based laptop and use a GPU from the laptop. Okay.
Yeah. So who do you have in the front seat listening?
Okay. Yeah. So what we have here, we have a Mr. Dummy Head with 2 binaural mics.
Okay.
As you can see, one ear, another ear.
Yeah.
I will once I quit talking, and my partner Basil will enable audio and share the audio to our audience. I will knock the door and everything. You can actually hear me bleeding into the car acoustics audio, so you will hear it. It's not like pre-recorded or pre-rendered, something like that.
Okay.
And essentially the demo setup is that you will experience as this Mr. Dummy Head guy will be listening at his position from the driver's seat, 2-zone audio, and essentially will be playing back 2-zone audio with equal sound pressure levels, equal RMS, whatever. And what we will be doing, we will be actively suppressing the other zone's audio supposed to be playing back for the rear zone for this head position as much as we can.
Okay.
Spoiler alert, we achieved on broader spectrum around 13 to 15 decibel of the compensation. It is a lot. It is a very bold claim, and we're not afraid to basically to claim it. And we already been demoing this vehicle to multiple professionals so far in California. Feel free to book the demo.
Okay.
All right. Yes.
ready.
So let me make sure I close the doors, and let me double check the microphones first. They should be all fine. Okay. So I'm gonna. There will be 2 scenarios. Before I allow my partner Basil to share the audio with you, there will be 2 scenarios. Number 1 scenario, we call it family ride.
Okay.
And essentially during the family ride, we will be playing back 2-zone audio.
Okay.
The front zone audio will be my favorite music band, AC/DC, and AC/DC track TNT. So
Okay.
I love to listen AC/DC when I grab my kids and I just drive them to school.
Mhm.
My problem is that they want to watch a Peppa Pig cartoon where sitting on the rear seats and watch them on the secondary row display. So
Okay.
so what I want to do, I want to remove Peppa Pig from my zone audio, right? So we
Yeah.
will be playing back solo, first AC/DC, then Peppa Pig solo, then we will play them back together, no compensation. So this will be very messy, right?
Okay.
Then we will turn on the compensation, and then we will turn it off and turn on again. That will be
Okay.
the very first demo case. And
Got it.
somewhere in the middle, I will knock the door, so you will hear me interjecting in the live demo, so you'll hear it. It's actually acoustics,
right.
but you can actually hear the fans of the Cybertruck. So it's all real, no worries.
All right. Well, we're ready. Okay.
Yeah, Basil, let's go with the first one.
Peppa has red spots on her face.
Mummy, I don't feel very well.
Oh dear, Peppa.
Okay.
So you heard it.
Yeah. We heard it with it on and off, and there was a little glitch at the end, but we did hear it finally on.
The glitch
So-
was that Cybertruck closed itself. I apologize myself. Yeah.
Okay. It shut it down. Okay.
Yep.
But yeah, I don't know about you, Dave. I heard we lost contact with Peppa Pig when we turned it on, so we couldn't hear about her spots. So, so it
I
was-
also knocked the door. If you heard
yeah,
it,
we could hear
many
that
times.
easily. That was easily,
Mhm.
yeah, it was easy to
Mhm.
do. So that was your estimate of around 12, 13, 15 dB of reduction. And what bandwidth were we looking at in terms of?
So we
frequency range?
claim it's around 250 hertz up to 8 kilohertz of the efficient range.
Okay.
We can certainly improve that with the time. Because our technology claims that we work with latencies as low as 30 to 50 microseconds.
Okay.
Yes, because of the PCI Express 4.0, 5.0, 6.0, they give you that level. So of the latency, you just need to come up with a low latency driver API technology to do so. That's what we do, by the way, in our low level foundational technology thing to unlock real-time audio compute. So that's how we can actually address higher parts of the spectrum of the compensation efficiently.
Okay.
And currently, the digital version of the same software goes up to 30, 35 decibel, and certainly digital cancellation of the digital signal and real acoustic ones with a ton of the non-linearities are different. But I want to tell you one story. The way we build the solution is the following. So it's not that much different from how
acoustic solutions are made by the other firms. So essentially what we do, we put this Mr. Dummy head near the headrest. We put these binaural microphones. Then we play back sine sweeps from each loudspeaker individually. We record the IRs, impulse responses. We move this Mr. Dummy head on, let's say, 2 centimeters. We repeat this procedure. And in the essence, we have the entire sphere near the headrest recorded. This way, we have a huge matrix of those original IRs recorded, right?
Mhm.
Then, somehow, I will not tell you how, we use a huge, gigantic matrix solver to generate the compensation IRs to deal with this whole thing, to compensate essentially and pre-render the whole thing, pre-render all the properties of the setup. That means how the sound propagates according to geometry of the car cabin, how the sound reflected by different surfaces made of different materials with different acoustic properties, how the sound is emitted by different loudspeakers with different characteristics and so on and so forth. We have it originally captured with those IRs. So when we generate the compensation IRs, we essentially also take this into account. So what we do afterwards, we take this gigantic matrix and we then load it in our GPU-based matrix convolver and run it real time. That's why we need GPUs here. So we essentially run 60 convolutions with a ton of the IRs, all convolving all together. And whatever the thing comes in between, let's say we want to process not the stereo signal, we want to process, I don't know, like Dolby Atmos multi-channel, or we want to capture immersive characteristics of whatever Dolby Atmos set up, or we want to add some custom whatever thing is, we just add more IRs and we multiply them with this matrix convolver, and it will not take any more linear computation effort to do so. So that's why GPU audio-based technology is the only way to make such kind of effective, efficient level of the compensation. And we have a second demo.
Yeah, let's hear the second one. What are we going to hear the second one?
Yes, so the second one, and I want to do this on purpose. So I want to complementary playback Chinese music, because we have
okay.
even though this is an English-speaking podcast, I know there are plenty of the Chinese colleagues of these APDA podcasts. I know you guys are very well connected, so I look forward to see you sharing this video and the fragment of the video with Chinese music played back and compensated. So this will be a little bit different and a little bit longer demonstration. So there will be 2 music zones played back simultaneously, front and the rear one. As far as I remember, on the front zone, there will be 1 Chinese music with the female woman's vocal voice on the front and 1 music. And for the rear zone, there will be a men's male voice on the rear. So essentially, we want to remove the men's music from the front zone, from the driver's seat.
Okay.
And then, so we will again start with solo zone 1, solo zone 2, playing back them together, no compensation, then turning on the compensation. And then after this, we will keep compensation on, and we will play back solo of the compensated zone at the driver position. So you will actually hear how much of the reduction we provide of the zone we canceling out at the driver's seat. Okay?
I think I got it.
Mm-hmm.
That's good.
All right.
Let's go for it.
DJ, turn it on. It might take a while to load the project.
I'll stop knocking the door and shut myself. So one thing, if you allow me, Roger, I would like to ask to share the screen with the GUI of the setup software, where we can, Basil, if or somebody, Spencer, is that you?
No, Basil can share if you.
Yeah. So if we can share the screen and our audience can see the screen. And we need somebody to confirm that they can see the screen. I then would like to, after confirmation, to ask my partner Basil to play back with compensation on, the part with compensation on. And I would like to invite the audience to look, to look at the master mixing panel, where they can see the SPL levels and all the knobs, all the master volumes are the same. We don't do any volume balancing, gentlemen. This is very important. I'm a little bit paranoid in terms of proving this all real, and we don't trick people and so on and so forth. So look at this. Basil, just play back with the, so as you can see, this is automation line. We just turn on the compensation, this is the purple one. Play back with the fragment real time with the, yeah, from there. Yeah.
Okay.
All right.
All right.
So yeah, we can stop screen sharing. Just a little bit for more proofs, you can visit my LinkedIn really quick. On my LinkedIn page, I used to record the same thing with my phone camera, which is absolutely a horrible way to record the experience. And yes, where you move the phone from one sphere near the headrest to another bubble, sound bubble, whatever, you can actually hear it. But between the bubbles, not in you can hear it if you move from one bubble to another, not in the space in between, because you don't guarantee what's in
Well, that
between.
was that was a question from our chat, is like, how big is that personal bubble and sensitive to head movements? So
Yes.
um, you can't, what you just said is you can't actually move from one to the next, but you can move around in it. And how, is it basically the size of the seat perhaps, or how big are you
Yes.
actually expecting to?
Yes.
Okay.
It's a very good question. So as everybody knows, this kind of technology, the physics and acoustics is based on the same principles, right? It's the same kind of the thing that many people do in active noise suppression, right?
Right.
Whereas the active noise suppression best in the industry achieve like 5 decibel deployed in Tesla vehicles.
Yeah.
We achieved here 13, 15 in this alpha version. I hope that closer to the CES exhibition, we can achieve around 20 or something decibel. So answering the question, it's around 15 centimeters bubble,
Okay.
and the bubble is dynamic one.
All right.
So that means this setup here, it's a horrible setup. And because we don't work with Tesla yet, we've done this as a reverse setup, okay? So we treat this whole acoustic setup and whole system as a black box system. We don't know how it works. We just push the audio through the loudspeakers, that's it, okay? When we work with the OEMs we partner with and integrate from the software level, we can definitely take into account many different aspects of the implementation, such as different head positions and postures and seat mounts and so on and so forth. So let's say if you move your posture and you move your seat, you incline, decline, you move your head, you can preload a different set of IRs also dynamically depending on what your decline incline position of your seat very easily. Or especially if you have an embedded camera in inside the cabin, that makes things way easier to track where the head is, to move this bubble, to actually load the proper IRs that were preliminary captured. Here, for this setup, we just took 2 bubbles to pre-compute, pre-render. But it doesn't limit us to pre-compute as many bubbles as needed.
God, that's great. Actually, this is a wonderful demonstration. Thank you. We've run over a little bit, which is okay. Not a problem. But go ahead, Dave.
Just out of curiosity, because I've heard this question before about electric vehicles, you said your consumption of the GPU is about 2 or 1.6%?
2%.
For the current generation, very big Qualcomm GPU, yes, 2.3.
Okay.
2.3.
So there's no in the naysayers to say that you're consuming too much power with the processing. That's not a concern.
Yes.
Yeah.
And I think the comment is if you get a bigger GPU or faster, then that percentage goes down
it
even
becomes
farther.
less of an issue.
Yeah, and we anticipate that evolution anyway, so that's good. We're starting in a good spot. Yeah, this is great.
Yes.
And you mentioned that you're going to be at CES. You're going to have your Cybertruck there. I'm assuming.
Yes, I hope I can make it to Nevada.
Good question. Good question. Bring a solar panel with you. But you're going to be in the Venetian Expo, level 1, Hall G. Okay.
Yes, thanks to Adam Levinson, who made right at the last moment. He helped us to get us in.
Well, Adam's one of our partners, so we're happy to hear that he could help.
Thanks, Adam.
Yeah. So your Hall G, and I got a number here. It's 60846. I think that's your booth number. So if anyone wants to check you out in January in Las Vegas, you'll be in the Venetian Expo, which it's essentially the Eureka Park, right? That's where that is.
That's correct. And feel free to reach out, Sergey, to arrange the demo.
Yeah, let's do that. That's everything. Was there anything else you wanted to make sure that we captured from you guys? But this was a great demonstration. Thank you very much. Appreciate that and the work that you put into it. And we hope for success there. Anything else from Sergey that you'd like to share?
Well, easier way to set up a demo is to write to info@gpu.audio.
Okay.
So we'll be happy to arrange time slots.
Okay. And that was info@gpu.audio. Is that right?
Yeah, I looked
We
up
got-
earlier. It's gpu.audio is their URL.
You got it. Thank you. We should have had it on the screen. Sorry about that. Great. We appreciate everything. And just from our side on the APDA, we'll be there as well. We're going to be borrowing Dave's suite, who's in the Venetian Tower.
Yeah,
So
you could check in over here.
okay, check in. Yeah, and we'll be back again in a couple of weeks in December 16th with another presentation from the APDA. Again with personal audio from BD Sound, so it'll probably be a different take and a different point of view, but there's also, we'll see what they have to say as well. This was lovely. I appreciate this. One thing I'll do for us as another request for anyone who wants to become a member of the APDA, please do. I'm going to bring up our screen and share that. You can join us, become a member at our webpage. Or you can also become a sponsor because we are a nonprofit organization and we depend on the support of our members and our sponsors. So we're looking forward to more and more membership and all of the support that we've been getting. So feel free to join us and continue to see what's going on here at the APDA. I'll leave that up just as I'll take that down. And we are thankful for everybody. I appreciate that. Once again, great presentation. That's Sasha. And we have Sergey from GPU Audio. Check them out at CES. Check them out on LinkedIn. You can see all of Sasha's wonderful videos there as well. And also email them at info@gpu.audio to get a demo at CES. And you'll see us there as well. So stay tuned for that. And we'll see you again very soon on here before we get to CES. Thanks, everyone, and take care. And I'll say goodbye now.
Thanks, everybody. Thank you.
Bye-bye.
Thank you.
Take care.
Okay.
Bye-bye.